sensitivity to the stick-breaking prior in Bayesian nonparametrics, and it's written by 4 authors who are all linked with either MIT or Berkeley or both, actually, most of them, because there seems to be a whole network which is very much very active, crossing the two coasts, if you want. So Ryan Giordano, who's going to be presenting the paper, is currently a postdoc, I think, in Tamara Broderick's group at MIT. Ryan received his PhD in statistics from UC Berkeley, where he was advised by Michael Jordan, Tamara Broderick, and John McAuliffe. And I think, if I'm not misinformed, Ryan will start as an assistant professor at UC Berkeley this summer. Shout if that's not correct, right? And then Runjing Liu is a finishing PhD student in statistics at Berkeley, advised by John McAuliffe. Michael Jordan is the P. Hong Chen Distinguished Professor at Berkeley. He's received many more distinctions and awards that I can list here in the time available. And in 2016, he was named the most influential computer scientist worldwide in an article in Science. Tamara Broderick is an associate professor at MIT who completed her PhD at UC Berkeley with Michael Jordan as her advisor. So Ryan will present the paper, and the paper will very soon be published as a discussion paper in Bayesian analysis in the upcoming issue, the March 2023 issue. So if you have any questions during the seminar, please write them in the Q&A section. Now, after the presentation by Ryan, we've got 4 very insightful invited discussions. And these are discussions by, the first one is by Steve MacEachern and Juhee Lee, then by Jim Griffin and María Kalli. Then there's one by María, Gil-Leyva and Ramsés Mena. And the last discussion is by Filippo Ascolani, Marta Catalano, and Igor Prünster. Now, after the discussants, the authors, in fact, Ryan, because he's the only one here, unfortunately, of the 4 authors, will present a brief rejoinder. If we have time left, we will then allow for questions, comments, and discussions from other participants. So please use the Q&A section, and maybe we can also allow for people to raise their hand if they want to talk. So finally, the last thing I need to tell you is that I just want to make everybody aware that this webinar will be recorded and made available as an ISBA resource. Okay, that's all for the boring introduction. So I give the floor to Ryan now, who can start with the presentation of the paper.
All right, can everyone see this?
Yes.
All right, let's see if I can present. All right, so I'm going to say this a few times throughout the course of this, but a big thank you to all the respondents and to the Bayesian analysis editorial board for making this possible. Having this discussion paper, reading through the responses and responding to them has been a great learning experience for me and a great pleasure. I'm really, really pleased to be here. We're going to be talking about assessing sensitivity to the stick-breaking prior in Bayesian nonparametrics. My name is Ryan Giordano. Runjing Liu is joint first author on this, and we were advised by Mike Jordan and Tamara Broderick. So I'm going to begin with a motivating example. It's a clustering problem in population genetics. We have genomic sequences from 155 individuals of the Taita thrush. It's a bird in Kenya. And we have microsatellite sequences of these birds at 7 different loci. And we're interested in using these genomic sequences to infer the ancestral populations of these birds. So this is a visualization of that model fit to this data. In this visualization, each vertical column represents a bird. So there are 155 vertical columns in this picture. And each color represents an inferred ancestral population. And each column, each bird is inferred to have some proportion of different ancestral populations. And so, for example, there's a green population that dominates this group of individuals, a red population, and so on. Now, you'll notice that there are kind of 3 primary populations, a green, a red, and a blue that comprise most of the sequences. But then there are also many small, rare populations. And it's a question of scientific interest to ask, how many distinct ancestral populations were there? That is, because we're modeling these populations as clusters, how many distinct clusters are there? And there are a few different versions of how you could ask this question. One, you could ask how many are there in this data set? You could ask how many populations are important in the sense that they're associated with more than some number of distinct loci observed in the population. Or we could ask the same question in a posterior predictive sense. How many different ancestral populations would we expect to discover were we to go back to Kenya and gather another future data set of exactly the same size or even larger? Furthermore, it's not just the number of populations, but also the co-occurrence of these populations that's interesting. So you'll notice that there are, additionally to the birds, there are also these black lines and these region labels. These region labels refer to geographic regions in Kenya, and I'm not going to attempt to pronounce them, but you'll notice that this region here is dominated by the green population, this by the red, and this by the blue. And there are kind of exceptions to this, right? So you notice there's a group of individuals here in the dominantly green region that have a little bit more than the expected amount of red. And similarly, in the red region, there's this group of individuals labeled B that have more than the expected amount of red. And phylogeneticists can take these exceptions as potential statistical evidence for historical migration of birds between these geographically separated regions. So this is scientifically interesting. We want to know which kinds of individuals tend to cluster together. Now, we're all Bayesians here, and so you can answer these questions with Bayesian posterior models. In particular, we'll be talking about discrete Bayesian non-parametric models that makes these questions: how many distinct clusters are there? Which individuals cluster together? Amenable to posterior Bayesian inference. But as with all Bayesian inference, the answer you get may depend on the prior you choose. And so in particular, here are three different priors that we might use. I'm not going to describe right now exactly what these priors mean, but I will throughout the course of the talk. Here is the prior. For those who know, this is the stick-breaking prior on the Bayesian non-parametric process, but I'll define that all later. This is the stick-breaking prior that we used to generate the data that you saw. Here in dark blue is shown a different prior that you might have used, and here's the resulting inference. Basically, there's no change. But here's a different prior, it's kind of point-wise as different from the original priors. The second one that produces quite a large change in these outlying individuals. This nearly erases this set of red outliers in the green region. So if you think that this prior is as reasonable as the one you actually used, then the evidence for migration from the green region to the red region produced by this set of outlying individuals is maybe what you would call not robust, in the sense that different reasonable subjective model choices would have given rise to different scientific conclusions. So how did we find these priors? That's going to be one of the main topics of this talk, how we identified these priors and identified in particular this one that erased this scientific conclusion. All right, so our problem is this: a discrete Bayesian non-parametric, I'm going to just say BNP from now on, model makes scientific questions amenable to Bayesian inference. Now, a model itself is not inference. To have inference from a model, you need to have some way of computing or approximating the posterior from that model. Today, we're going to be using variational Bayes. I'll be describing what variational Bayes is and how we use it. And we want to know how sensitive our variational Bayes or VB approximation is with its resulting inferences to our BNP model choices, in particular our choice of the prior. Now, a reasonable solution you might think of is, well, I'm going to pick a bunch of priors and I'll just rerun VB for each of my candidate models, each of my candidate priors. Well, there are two problems with this. One is, even though VB tends to be faster than methods like Markov chain Monte Carlo, it can still be quite computationally expensive. And so it might not be possible to run it a large number of times. But there's a deeper problem, which is here, when we're trying to specify a prior density, technically that space is infinite dimensional. There's quite a large space of potential priors to explore. And so even if we can run our approximation a large number of times, we need some guidance as to which finite number of prior densities we should choose. And so we're going to propose to address these problems using a linear approximation, which efficiently estimates the BNP sensitivity from a single run of VB. Now, this linear approximation can be used in at least two different ways. First of all, if you can't actually rerun VB at all, it can provide approximate sensitivity without refitting, or if you're able to refit, it can guide the choice of priors, particularly alternative prior densities, for careful evaluation via refitting. All right, so with that motivation in mind, here's the outline of the rest of the talk. First, I'm going to present the Bayesian nonparametric model that we consider and which prior we're perturbing. I'm going to introduce the variational Bayes approximation to our BNP posterior. Then we'll talk about forming our linear sensitivity approximation to scalar hyperparameters. And then I'll extend that result to sensitivity to the functional forms of the prior. And finally, at the end, I'll revisit our Taita thrush example and show how we found that adversarial prior. Okay, so it will be helpful to discuss, to develop intuition in the context of a qualitatively similar, but much simpler model than our Taita thrush genomics example. And that model will be the Fisher-Iris data. And the Fisher-Iris data, like the Taita thrush, consists of measurements of individuals from distinct species, except instead of birds, it's flowers, and instead of genomic sequences, it's physical measurements of the shape of the flowers. So we have 150 flowers, 4 different measurements, and the first 2 principal components of these measurements are shown here. And we happen to know that there are actually 3 distinct species of flowers. Perhaps you can see there's kind of 3 distinct groups. But let's suppose that we didn't know that. Could we infer from these measurements alone how many distinct species are present here? Now, this is a lot like the thrush example. Instead of genomic sequences, we have physical measurements. Instead of birds, we have flowers. But otherwise, it's qualitatively similar. A Bayesian clustering approach to this problem assumes that measurements from a particular species cluster together, and we can place priors both on the frequency of species in the population and the shapes of the distributions of their measurements within a species. A Bayesian nonparametric approach says that in principle, were we to go out and get an infinitely large amount of data, the number of species in future data sets could in principle be infinite. Now, in order to use such a prior, we need a prior on the probabilities of an infinite number of species. And here a species corresponds to a particular component or potential cluster in the model. How do BNP models do that? Well, particularly canonical BNP model is called the Dirichlet process, or DP prior, and that allows an infinite number of components. And I'm going to have to introduce a little bit of notation. We're going to let pi k denote the prior probability of component or species k. We've got an infinite number of these, and they have to sum to 1 because they're all prior probabilities. And we need to specify a prior on these so that these pi's themselves are random, they're valid probabilities, and they all sum to 1. A widely used way to represent this is called the stick-breaking prior. And here's how the stick-breaking prior works. We're going to start with a unit length stick. It's a unit length because it represents the total amount of probability in all of the components. We're going to draw a random stick length to break off from a beta 1 alpha distribution. So this is a random length. We break it off of the unit length, and we're going to call the amount that we break off pi 1. That is the probability of the first component or species. This is a random probability. It's random because this is a prior distribution. Now we've got some amount of stick left. The amount that we have left is 1 minus nu1, or the length of our first stick. We draw another amount to break off, again from the same beta 1 alpha distribution, break it off from what remains, and call that amount pi 2, or the prior probability of our second component or species, and so on. And we keep drawing new lengths from the beta distribution. We get an infinite amount of them. We break them off of the amount that remains, and so on. And this represents a prior on this infinite dimensional set of pi's, or the infinite dimensional simplex. Now, posterior quantities, because it's Bayesian inference, depend on the prior. And this prior is entirely specified by the density of the stick-breaking process, which in this case, we're taking to be the beta 1 alpha distribution. Now, if you're going to use the Dirichlet process prior with the stick-breaking representation, you have to make some decisions. If you're going to draw these stick lengths according to the beta 1 alpha distribution, what should alpha be? Of course, you can try to elicit it, or you can use empirical Bayes, but no matter what you do, typically there is some range of alpha parameters which are subjectively reasonable. And you want to make sure that your posterior inference isn't excessively sensitive to that range. But furthermore, why do we use the Dirichlet process in a context like the Taita thrush? Well, in reality, in most cases, probably in all cases, it's for analytical convenience and because the Dirichlet process prior is widely studied. Why should this density even be in the beta family? If slight functional deviations from this density also give rise to excess posterior sensitivity, then that itself might be worrying. So that's the model that we're going to be studying. We're going to be particularly focusing on the stick-breaking prior. What's our posterior approximation scheme? So we're going to use a method called variational stick breaking. And in order to discuss this, again, I'm going to have to introduce a little bit more notation. Throughout the paper, I'm going to let the variable zeta denote all of our posterior model variables. Now, this will include the stick lengths that we just saw, and the stick lengths effectively determine our component or species probabilities. We're going to have indicators that indicate which individual came in the model from which cluster. And then we're going to have the parameters governing the cluster shapes. We'll let X denote our observed data, and then we can compute our posterior, the probability of our model parameter zeta given the data, and that's intractable. So we're going to approximate our posterior using a class of distributions Q over the same parameter zeta, but parameterized by some finite dimensional parameter eta. And these Q in general are going to be simpler than the true posterior. They're going to be simpler according to two simplifying approximations. First of all, within these Q, we're going to use a large but finite number of sticks. This is a truncation approximation. And second of all, within the Q, we're going to model the sticks, the assignments, and the cluster shapes as independent for one another. And this is known as the mean field approximation. And the reason we make these approximations is it allows us to numerically solve this optimization problem, where we find the parameters eta that place Q closest to our true posterior in KL divergence. Right, so if we hadn't made these simplifying approximations, we couldn't evaluate the KL divergence and we couldn't find the closest distribution. Now, once we've found the parameters eta, which are what we'll call our VB optimal parameters that give the Q closest in KL divergence to our true posterior, we take Q at those optimal parameters to be our VB approximation to the posterior. So this is our approximation scheme. We minimize a KL divergence to the true posterior by solving an optimization problem, which is made tractable by our simplifying assumptions or approximations on the family Q. Right? So taken in total, this BNP model and the VB approximation, we've defined a map from our prior to a posterior summary. Let's take our alpha in the Dirichlet process as an example. The posterior depends on the prior. And we're going to emphasize this by writing our posterior as depending on the prior in the conditioning. In particular, it depends on our prior, our parameter alpha in the stick braiding beta distribution. Because the posterior depends on alpha, the KL divergence depends on the prior alpha. So I'm going to emphasize that by writing KL depends not only on the variational parameters, but also on the prior parameter alpha. Because the KL divergence depends on alpha, the optimal variational parameters depend on alpha. And I'll emphasize this by writing eta hat is a function of alpha. And because the optimal variational parameters depend on alpha, the posterior quantities of scientific interest depend on alpha. So for example, the expected number of clusters is a posterior expectation over the optimal variational distribution, which itself depends on alpha. Or that whole picture of ancestral species that I showed you at the beginning is a particular functional of the variational distribution, which itself depends on the optimal variational parameters, which depends on alpha. So we've defined a whole procedure that maps the prior to a posterior summary. And we want to know how these final scientific outputs depend on aspects of the stick-breaking prior. For example, the parameter alpha that we chose. Okay, so how do we do this? Well, I'm going to step back from alpha and say, all right, we're going to do all the same stuff, but we're going to have T be some generic real valued hyperparameter for the stick breaking density. T could be alpha, but later I'm going to take T to be parameterized more generic classes of perturbations. So as with alpha in the previous slide, our optimal variational parameters depend on T. Now, our whole problem is that explicitly evaluating the dependence of our optimal variational parameters on T requires solving a new, potentially expensive optimization problem. So instead of solving that optimization problem, we're going to approximate the dependence on T with a first-order Taylor series expansion. We're going to pick some base value of the prior, which we can, without loss of generality, call T equals 0. And we're going to say the dependence of our parameters on T is approximately linear. And in order to express the linearity, we need to calculate this derivative of our optimal variational parameters with respect to T. Well, is this differentiable? This whole procedure is through an optimization problem. We come to our first technical result of our paper, which is yes, under regularity conditions, on the objective that we specify, the map from our prior parameter to our optimal variational parameters is in fact continuously differentiable at T equals 0. So we can form this approximation, and furthermore, because it's continuously differentiable, there's reason to believe that it provides a good approximation to the true dependence on T, at least in a small neighborhood of the original prior. All right. Now, I'd like to call attention to two facts. First of all, only one part of this process is really computationally expensive, and that's the solution to the optimization problem. So we only really need a linear approximation to the map from the prior to the optimal variational parameters. We can retain any nonlinearities that exist in the map from the optimal variational parameters to the quantities of interest. For example, the map to the expected number of clusters is actually highly nonlinear as a function of eta, the variational parameters. And we can retain those nonlinearities because that's quite fast to evaluate. Second of all, you might be worried about whether you can actually evaluate this derivative. It turns out it's quite tractable. We give a closed form for the derivative. And as will become important in the rejoinder section of this talk, it's actually quite easy to automatically compute using modern automatic differentiation, using stuff that you had to implement in order to form the VB approximation in the first place. But I won't talk too much more about the implementation in this talk. All right, so let's step back from generalities and talk about the iris data. We formed a BNP model with a VB approximation to that iris data. We picked alpha equals 6, which gives a reasonable prior probability of the expected number of clusters and fit the model. Here's a posterior mean fit. We actually recover the expected 3 clusters. Using theorem 1, we compute the derivative of our optimal variational parameters with respect to the alpha parameter, evaluated at alpha equals 6, the one that we used to form our initial fit. And using that derivative, we approximate the optimal variational parameter at different alpha values. So let's see how we did. Whoops. Let's focus on this graph on the left. On the y-axis, I've got different values of the Dirichlet process parameter alpha. This red line shows the value 6 that we actually used to form the initial approximation. On the y-axis, I've got the expected number of in-sample clusters. That was the expected number of actual species present in the iris data. And you'll see that the range is actually quite small on this y-axis, ranging from 3 to about 3.6. This blue line shows the effect of actually refitting the model for each of the different alpha values. So for each of these triangles, we actually reran a new optimization problem. So this was a slightly expensive curve to compute. You can see that as the alpha parameter ranges, we go from about 3 to 3.4. So this is actually pretty robust to the alpha parameter as evaluated by refitting. The red line now shows the same quantity, but as evaluated using our linear approximation. So in order to compute this red line, we only computed one fit at the vertical red line with alpha equals 6, computed a single linear approximation, and then computed the rest of these dots using that single linear approximation. Now, the first thing you might notice is that this linear approximation is super nonlinear. Again, that's because we only linearize the solution to the optimization problem. The map from the variational parameters themselves to the expected number of clusters is still nonlinear. So the linear approximation actually deviates from the ground truth a bit as you get further from the point at which it's evaluated. It's the kind of thing you expect from all series approximations. But importantly, you see that it captures the correct qualitative behavior, which is that this quantity is actually quite robust to the alpha parameter. We get a different story if instead we look at the posterior predictive. This is asking, were we to go out and gather a new data set of the same size, how many different species would we expect to find? Here, the y-axis range has changed. It now goes from 3 to 8. And you can see that the posterior predictive actually varies quite widely as the alpha parameter ranges, and both the linear approximation and the actual refitting capture this behavior. So here are two different quantities, one robust, one not robust, within the same problem, and the linear approximation captures very cheaply the right qualitative behavior that we can verify with an expensive refitting process. Okay, great. So that's how we might compute sensitivity to scalar valued hyperparameters like the alpha parameter. What about stick-breaking priors that aren't in the beta family? Well, in order to use the machinery we just developed, we need to do something like parameterize a path through the space of prior densities. And here's how we're going to do that. I'm going to have to introduce a little bit more notation here. Let's let P0 denote some initial stick-breaking prior density. So for example, you can take P0 to be the beta density with some particular value of alpha, say alpha equals 6. And we want to replace this density, P0, with some alternative density, P1. That could be another beta density, or it could be anything, just some generic density on the unit interval. So I'm going to define a perturbation phi so that a perturbed stick-breaking density, remember nu is the actual length of an individual stick. The length of the prior on an individual stick, given this function valued perturbation, is proportional to our original density times e to the phi. So because we've got e to the phi, we're guaranteed that this density is positive, and because of this constant of proportionality, there's an implicit normalization that happens here. Now, if we take phi equal to the log difference between our new prior and our old prior, then this is just a new way of rewriting P1, because the minus log P0 cancels with this leading P0, and we're left with e to the log P1, which is P1. So having done this, we've done nothing but rewrite P1. The value of doing this is that by, whoops, I hit my mouse there. The value of doing this is that if we take t to be some scalar parameter at 0, 1, and the map from t to p on the stick given t times phi parameterizes a smooth multiplicative path from our original prior to our alternative. When t is 0, we're just multiplying by e of 0 and we get back our original prior. When t is 1, we just get phi, which gives us p1, our alternative prior. And I've shown this path in these plots. If we let our original prior be shown in light blue and our alternative prior P1 in dark blue, the steps in between are evenly spaced steps as t goes from 0 to 1. Because it's a multiplicative perturbation, you can see that they're not evenly spaced in the space of densities, but they are evenly spaced in the space of log densities here. So we parameterized a path. Now, for any particular phi, we can then try to apply our theorem 1 to the map from t to our posterior, and everything's fine. All right, so that's great as long as we actually have only one particular alternative prior in mind. But what we actually might want to do is we might want to use these derivatives to search the space of alternative priors, right? So we want to find values of P1, alternative densities, which have a big effect on our posterior quantity of interest. Now, that might raise some concerns. Can we find some large classes of phi for which we can even apply theorem 1? But even more worryingly, when we search over an infinite dimensional space of perturbations, do we break the validity of our derivative? That is, we might be worried that even though for any particular phi, the function is differentiable, maybe the residual of the linear approximation behaves arbitrarily badly as a worst case over all particular functional perturbations. So we alleviate this worry with our second technical result, theorem 2, which is that under the same conditions as theorem 1, the map from this generic function to our optimal variational parameters, viewed as a map from the space L infinity to the finite dimensional space of variational parameters, is continuously Fréchet differentiable at the 0 function. So important in this is the choice of space, L infinity. L infinity is the vector space of bounded Lebesgue measurable functions on 0, 1 associated with the supremum norm. And that means the supremum norm is denoted L infinity. That means we consider the size of a multiplicative log perturbation to be the point-wise largest value that it takes on the unit interval up to sets of measure 0. And Fréchet differentiability means that first order Taylor series approximation provides a uniformly good approximation to our underlying function, as long as we restrict ourselves to one of these L infinity balls. Now, interestingly, in the paper, we talk about many other classical choices of norms and paths actually aren't Fréchet differentiable. That is, you don't have a uniformly good linear approximation, and no matter how small you make your ball, your derivative will be misleading. And so for that interesting technical result, I'd refer you to our paper. But importantly, this concern about Fréchet differentiability actually isn't an idle one. It's something that you really do have to worry about. All right, but we'll take it for granted going forwards and restrict our consideration to this L infinity norm. And now, now that we're sure that we can do this, how do we actually do it in practice? Well, if we have a smooth quantity of interest, for example, the expected number of clusters, we can define our local sensitivity of that expected quantity of interest G to a particular perturbation phi as the derivative of that quantity of interest in the direction phi. And we can ask what phis have large derivatives for our particular quantity of interest. Well, it turns out that we can actually explore this space easily as a corollary of these two theorems using a quantity called the influence function. So it turns out that this derivative, the sensitivity of a particular quantity of interest with respect to phi, takes a super nice form. It takes the form of an integral of a quantity called a function called the influence function against the perturbation phi. It's just a linear operator with an integral, and you can compute this influence function and you can look at it. So here's an example of what the influence function looks like for the iris data for the expected number of clusters. So let's start with this left plot. This is actually just a plot of a base prior. This is actually a stick breaking prior with alpha equals 2. On the x-axis, we've got the stick length that goes from 0 to 1. On the y-axis, we've got the prior density. This is, again, the beta distribution with alpha equals 2. It will be convenient to visualize the influence function not on the unit interval, but on the logit transformation of the stick lengths. The reason is the influence function tends to get bunched up on the ends of the interval. So this is the exact same density, except the x-axis is now the entire unit interval, and it's the logit transform of the stick lengths. So this is the logit stick length. The y-axis is now actually the exact same density here, but taking into account the Jacobian of this transformation. And this is the influence function, where again, the axis is the logit, the x-axis is the logit of the stick length, and the y-axis is the value of this influence function. So this purple curve, if you integrate it against a log perturbation in the stick space, that gives you the sensitivity of the expected number of clusters in sample to that particular perturbation. And you can see that this influence function looks a bit crazy. It's got negative lobes, it's got positive lobes. Why does it look like this? I have no idea. It's actually quite a complicated map from the space of priors to the output. But we can use it to design perturbations that do what we want. Let's see how that works. So again, right here, we've got the same graph. We've got the x-axis of the logit of the stick proportion. On the y-axis, we've got the value of the influence function. And now I've placed a perturbation phi. So this is of the value of a log perturbation shown in black. And I've taken this phi and I've lined it up with one of the positive lobes of the influence function. Right? Now, a particular phi, a perturbation, defines an alternative prior. This is what that alternative prior looks like in the original space, shown in dark blue. And if we were to use this prior, here's what we get. On the x-axis is t as we go from 0, no change, to 1, which is completely replacing the original prior with our new prior. On the y-axis is the expected number of in-sample clusters. You see, as expected, changing from our original prior to this new prior increases the expected number of clusters. It increases it because we've aligned our perturbation with a positive lobe of the influence function. So when you integrate these two things together, positive times positive is positive, and you get a positive perturbation. The linear approximation, again, is shown in red. The exact refitting is shown on blue, and the two line up very well. Here are a couple other perturbations. The one that we just saw is now on, The one that we just saw is now on the bottom. Let's suppose we instead line our perturbation up with a negative lobe of the influence function. We integrate this perturbation against the negative lobe. We're going to get a negative change. Dark blue is the alternative prior. And sure enough, we actually end up decreasing the number of expected clusters. The linear approximation, the refit match. If we design a perturbation that lines up with both a negative and a positive lobe, this is what the alternative prior looks like. We end up having very little change because the positive and the negative lobes cancel out with one another. So by using this, we can design priors that do things that we want. And I would argue that by looking at these three priors, you might not guess a priori that they do exactly what you want. As a matter of fact, you can see that there are these extra negative and positive lobes. It's not just a matter of shifting mass left or right. You could design priors that add mass to the right and decrease, and also add mass to the right and decrease the expected number of clusters due to the complicated shape of this influence function. So you don't really have to understand how the influence function arose to use it in this way, to detect which kinds of prior perturbations are influential. All right. So all of this has been in the context of the iris data for expository purposes. We can do all of these exact same things in much more complicated settings like the Theta thrush. Oh, I'm sorry. I forgot one other thing that I would like to do with the iris data. We have just been using the influence function to design kind of bespoke perturbations. We can also do things like find what is the worst case perturbation in an L-infinity ball. Why L-infinity ball? Remember, that's because we know that we're Fréchet differentiable in L-infinity balls. An L-infinity ball is just a log perturbation phi that is pointwise no larger than some particular value. We can actually just read off what the worst case perturbation is from the influence function. So if we're going to look at an L-infinity ball of unit length, that means our perturbation phi can't pointwise take values that are greater in magnitude in 1. What's the function that's pointwise in no larger than 1 in absolute value that has the largest integral against our influence function phi? Well, it's just the sine of phi, right? So we're going to make our perturbation negative 1 whenever the influence function is negative. We're going to make it positive 1 whenever the influence function is positive, and so on. You can see there's a weird little dip here where the influence function briefly goes negative, positive, negative again. Shown in dark blue is the alternative prior density that results from this. This is a crazy looking prior density. It's maybe not something you would choose, but this is the worst case density in this unit ball. This is what you get. As you expect, it produces a positive change. If you remember the x-axis from, or the y-axis from the previous plot, this is in fact larger than the other changes that we designed, but it's still actually not numerically very large. You know, this is a change in the expected number of clusters about 0.03. Now this worst case prior actually looks kind of unreasonable. I don't think it's a subjectively reasonable prior, but the fact that the worst case sensitivity is small is strong evidence of robustness in this case. So if you remember, we came to the conclusion that the expected number of in-sample clusters was robust to the alpha parameter. The fact that the worst case functional perturbation that itself looks kind of crazy, that we're also robust to that fairly extreme perturbation is pretty strong evidence that the in-sample number of clusters in the iris data is actually robust even to function valued perturbations of the stick-breaking prior. So this is a strong robustness result for the iris in-sample number of clusters. Okay, now with that having said, we're now going to move on to apply these ideas to the Theta thrush example. So I'm now going to say a little bit more specifically what we did. We adopted FAST structure as like a topic modeling model for genomic sequencing data to Bayesian nonparametric prior, and we study the Taita thrush. We form an initial fit using alpha equals 3 in a Dirichlet process prior. And this is the fit that we showed you at the beginning of the presentation. And we're going to examine deviations from this initial fit, both parametrically and non-parametrically. So first, let's look at the same thing, the expected number of ancestral populations in this data set as a function of alpha. So this is exactly like the first graph that we looked at for Fisher iris. On the x-axis, we've got alpha. This is the initial fit at alpha equals 3. As before, red is our linear approximation, blue is the refit. You can see that here the y-axis ranges from about 4 to 20. So this is an extremely non-robust quantity. If you want to ask how many distinct ancestral populations do we find in this population, it's super non-robust, even just to the alpha parameter. But we can kind of robustify it by asking modifications of this question. So if we were to ask instead, how many distinct ancestral populations are present in at least 20 loci. By loci, I mean loci of particular individuals. Then by thresholding that at 20, we come up with something that ranges from only 2 to 4.5. And if we ask for 40 individual loci, we come to a quantity that's actually quite robust. And again, I'll call attention to the fact that refitting and the linear approximation are not right on top of one another, but capture these qualitative conclusions of robustness and non-robustness quite well. Because this is a much more expensive model to fit than the Fisher iris, these blue curves were actually fairly expensive to compute, relatively speaking. At the very end of the talk, I'll talk about computation. Okay, what about function-valued perturbations? So remember this evidence of intermigration between the green and the red regions. Let's focus on this set of red outliers in the green region. Can we eliminate this by choosing different functional forms of the stick-breaking prior? Now remember this plot that we showed where this is the original prior. This is alpha equals 3. This is a prior perturbation that doesn't change this much. This is a prior perturbation that mostly makes it go away. How did we find these? As you might guess, we found it by looking at the influence function of the total proportion of the red population amongst these outlying individuals. Here's what that influence function looks like. The x-axis is again the logit of the stick proportion. The y-axis is the value of the influence function for the expected proportion of the red population within these outlying individuals. Here's our original prior. If we design a perturbation that overlaps with both the negative and the positive lobe of the influence function, we get this alternative prior in blue, which as expected has very little effect on these outlying individuals. However, if we define a perturbation that overlaps, that is mostly large when the influence function is negative, and mostly negative when the influence function is large and positive, we come up with this alternative prior, and sure enough, it decreases substantially the amount of red in this set of individuals. Now, I'll emphasize something that I think I didn't mention before. This is actually the effect of refitting with these priors. I'm showing you here the actual refitting, not the linear approximation. So this really does produce the change that the influence function predicts it does. What about these green outliers in the red region? It turns out that even by constructing this worst case prior, this is the influence function for the proportion of green in the individuals of B. It's different than the other one, but we can construct a worst case multiplicative prior. It looks totally crazy. This is not reasonable, but this is the effect that it produces. It's basically unable to remove the green population from these individuals. So it turns out that these green populations are quite robust. These red populations are actually not. And these predictions from the influence function are borne out by the act of actually refitting with these alternative priors. Now, I want to emphasize in only one slide, and probably this point deserves more than one slide, that the linear approximation isn't perfect. So here we've got our initial fit for these red individuals. This is what we actually refit with when we refit with the alternative prior. And this is the linear approximation for the same prior. Now you'll notice that there's this one outlying individual, n equals 26, that when you refit with our alternative prior actually gets much more of the red population that isn't predicted in the linear approximation. So this single individual is actually like very badly approximated by the linear refit. And this is a possibility, right? These linear approximations aren't perfect. And whenever possible, it's important to verify their predictions by refitting. In particular, we would like to recommend these procedures as guides for more accurate and believable verification procedures, in particular by actually rerunning your optimization whenever possible. All right, I'll close with some brief computation considerations. So for this Taita thrush data set, to run our initial fit, that is to fit the VB model, took about 7 seconds. In order to solve the linear system required to compute the derivative for our alpha hyperparameter sensitivity, it took about 0.3 seconds. And then once we've done that, to evaluate the linear approximation for all of the different values of alpha, it took fractions of a second. Really computing a single linear solve is the computationally expensive part of this. Running all of the refits using warm starts took about 30 seconds. So by using the linear approximation we solved, we saved quite a lot of time. For the non-parametric perturbations, the function valued perturbations, computing the influence function took about a half a second. It's a little more expensive, but not that much more expensive than forming the hyperparameter sensitivity. Solving it for a particular perturbation cost another half a second or so. And then rerunning the linear approximation was essentially free. Running all of our refits for a particular perturbation took about 10 seconds. Now, importantly, this doesn't take into account the fact that it would have been hard to find these perturbations in the first place without having the linear approximation. But even within that context, it's still faster to use the linear approximation than to actually refit. All right, so that wraps up the substance. In conclusion, we provide a tool to efficiently evaluate the sensitivity of a BNP variational posterior to prior choices. By linearizing the variational parameters, we can provide a reasonable alternative to re-optimizing after model perturbations. And this influence function can provide guidance for finding particularly sensitive model perturbations, which you can then investigate more carefully by actual refitting. But perhaps most importantly, it is easier now than it's ever been to use local robustness techniques, right? These are quite old ideas in a lot of ways. They've been around for a long, long time. We're repackaging them in a particular context, BNP models and variational Bayes, but we're taking advantage of a lot of modern computational techniques that weren't around before. In particular, high-quality automatic differentiation makes this quite easy to do, and it would be quite easy to do in your own setting too. And we'll talk about that, I think, a little bit more in the discussion and rejoinder. So I am so pleased this is forthcoming in Bayesian analysis. I'd also like to call attention to JAX, which is the automatic differentiation package that we used in order to implement all of these. And with that, I'll wrap up and we can begin the discussion.
All right. Thank you, Ryan, for a very, very clear and extremely well-timed presentation on the dot, really. So that's wonderful. So we have, as I said, 4 invited discussions. And I'll take them as they are as they will be in the published paper. So Steve and Juhee, yours is first up. So whoever wants to take the take the presentation forward, are you going to do it, Steve?
I will jump in. I don't think I have screen share privileges right now.
Ah, that's interesting. You don't have this sort of green thingy down at the bottom which says share screen.
We do, yeah.
Okay.
So there we go. There we go.
You've discovered my lack of competence.
No.
First off, we just thought this was an absolutely tremendous paper, and as Ryan says, some of these ideas have been around for a while. Looking at influence has been big in classical statistics for a long time, and there are Bayes versions of things as well. And yet to really combine it with the modern computation and automatic differentiation takes everything to a new level. And I think we see that in this particular application, but there are so many more where the same ideas will just have an absolutely huge impact. When I think about applied statistics, really working on serious problems, we're always looking for tools, right? And we have a great selection of tools that we learn in all the standard courses, and we're comfortable with them. We use them, we teach them, and they really work. And yet the very best of those tools not only provide a tool for one analysis, but they change our thinking about problems. And I think that this paper is one of those papers that's going to do that. It's not just here's a particular model and we have one model, and if you do this, you find out about sensitivity to the stick-breaking prior. It really is saying here's this new territory and use these tools and use them broadly. Sensitivity analysis is wonderful. But in many cases, the version that you want to get to is not just trying a few priors haphazardly, but really looking for where the particular sensitivities or deficiencies in your model are. And that's part of the wonderful work in this paper, the mathematics that accompanies the computation, is it really does say, here's how you find directions of weakness in your model, weakness for the inference that you want to consider. And that of course, is just core for good applied statistics. BNP models. What I'm going to do is focus on one little piece of what we see in our discussion. Other discussants may have much to say, I'm sure, as well. But for the Fisher's iris data, for example, one that we all know the data set, and we all know the structure of the problem. The basic model that they've written down is kind of a smooth version of a Dirichlet process, where it's not discrete data itself, but you observe, multivariate normals that are driven by the cluster locations. And when I think about all of these non-parametric Bayes models that are in the sort of smooth version of a countable mixture model, there's always a question about the prior distribution. And of course, we do know that the prior distribution has a big impact on some inferences that come out and not a big impact on other inferences that come out. I think that there'll be commentary on that later on. But, for me, part of the message that comes out of this work and other investigations is that we should be very careful about the form of the prior distribution that's written down. And so there's kind of a standard formalism that people write down. It actually goes back to Antoniak's old paper on mixtures of Dirichlet processes, sometimes missed in that paper. Jim Griffin has a different split, a different prior distribution about the smoothing part versus the Bayes measure, which we found works very, very well in a lot of problems. One that Juhee and I have worked on is to change the structure of the prior in a different way. So rather than thinking about a prior distribution, perhaps on the mass parameter, in a separate prior distribution on the dispersion of that Bayes measure. And notation is different in different, so beware of the meaning of alpha. We tend to favor something that focuses on what we would call local mass, which really puts the emphasis not on the prior distribution, but on the posterior. If you have data and you have a likelihood, what will things look like after you look at that likelihood? And here are some quick results, and then I'll disappear, so for timing. The top row has independent priors on the mass parameter and the dispersion of a Bayes measure, just a basic model. It's loosely the form of the iris data. It's not the iris data, different. The number of clusters, the distribution changes dramatically. For a prior that focuses on local mass, you would change the dispersion and you change the mass as well simultaneously. Number of clusters is very, very stable for the parameter. And it's not only that, here's one that does the same thing, looks at posterior means for different things. It's a different data set than the earlier one. In one case, independence priors. This is a well-calibrated Bayes measure or an over-dispersed Bayes measure. People often do this in practice. Completely different sorts of inference. If you look at the same where you have a local mass parameter, the well-calibrated prior has real shrinkage. The over-dispersed version, there's not much shrinking. You see the same pattern. So the structure prior, we think, is really a big thing and deserves more consideration, not only for Dirichlet process models, but many others as well. I will sign off because I've taken too much time. Next discussant.
You've taken exactly the right amount, Steve. So it's perfectly timed to 5 minutes. So that's wonderful. So Jim and Maria, do you want to go ahead with your discussion, please?
Yep. Let me see where we are. Okay. View. So can you see the screen?
Yes, thank you.
Okay, great. So I won't delay. I'll say that this is indeed a stimulating paper because it shows us how automatic differentiation combined with variational Bayes can be used to understand local sensitivity to the hyperparameters in the Bayesian non-parametric priors. The fact that you have the automatic differentiation with the VB that allows the model to be fitted once, and then you can use that to find the worst case non-parametric priors is great. And what I'll say is that we have a situation where we have the Dirichlet process prior. So we have the constant beta of 1 alpha. So can we consider extensions to other priors like the Pittman-Yaw, where you don't have your constant beta, or like a general stick-breaking prior? So moving on, I'll just talk about an application to density estimation, since Ryan was looking at clustering. So we've looked at the example of Griffin in 2010, where we have the following. You can see the parameterization of the Dirichlet process mixture. The point I'm making here is the smoothing parameter alpha, because that determines whether you're going to end up with something that has a single mode, and that's if alpha is really large or close to 1. And if A is far from being 1, then you end up having a multimodal setting. So this is the setup by Jim. I'm trying not to say Jim Griffin, and I'm just say by Jim. And obviously we use it on the well-known galaxy data, and we look at different values of this smoothing parameter A. So what you can see basically is the following. As A gets larger, we end up having a single mode. So that's the dot dash line. And if you have small or relatively small values of A, you get 2 modes. Okay, so what have we done in terms of the sensitivity? So we consider the sensitivity to A by adapting theorem 1 of the paper and using a specific value of A, and we call that A naught. Then what we did was to fit the variational Bayes algorithm 100 times to avoid problems with local modes. And this is what we have summarized in this slide. So we've got the refitting, which is the solid line. We've got the optimal VB, which is basically when we choose the optimal variational parameters for the alpha and then extrapolate. And then we have all the 100 VBs where we extrapolate first, and then at each alpha, we find the optimal variational parameters. Okay, so these are the values of A, I say alpha, of A0 and the kind of increase. And these are the values of X, which is where we saw the issue with the double modes and the single modes. So to point out what we have is that with the refitting, we see that there's a change point that is close to values of alpha that are probably 0.03, 0.04. When you use the optimal VB, when alpha is small, it doesn't really pick that up. And it's the same with the all 100 VBs. However, when you move on to the all 100 VBs, you can actually see that the dash line actually picks up the threshold as the alpha gets bigger. So to summarize the sensitivity to this alpha naught, the approximation works well locally. We find that having a large range of local modes can improve the performance over a wide range of alphas. And the wider range of local modes could be achieved by using several different alpha zeros. So basically we could, for example, choose different alpha zeros, and instead of running the algorithm for 100 runs, do it for 20 each, and then you can get a wider range of local modes, and that could be more informative. And to conclude, so I can give time to the next discussion, is that with the automatic differentiation, we can get the gradient of elbow with respect to the variational parameters, and perhaps we can actually use that to get empirical estimates of the hyperparameters, and maybe that would tell us something. And I'll leave it to this and pass it on to the next discussant.
Lovely. Thanks very much, Maria. Okay, so the next discussant, the next discussion, we have another Maria and Ramsés, who's going to speak. I don't know, but between the two of them, they'll sort it out, I'm sure.
I'll speak.
Good, excellent. We can see your screen.
Yes. Let me put it in full screen mode. Can you see that? Can you see it?
Yeah, now we see it perfectly. Yeah.
Thank you. So first of all, congratulations on the very nice paper. We really love reading it. We love the mathematical framework. We learned a lot from it. And we agree also with Steve and María and Griffin and Juhee that it's a very important problem you're tackling here, because sometimes in Bayesian and Nonparametrics, when choosing the hyperparameters, sometimes we do it somehow blindly. So congratulations on the topic. So our discussion goes in this direction. You work on the class of stick-breaking processes where these sticks or length variables or breaks are IDD, right? But the stick-breaking world is huge. Some famous processes that have a stick break in the composition are normalized random measures with independent increments. And for example, for those very interesting processes, it is well known that not all the time the sticks are ID, right? So our discussion goes in this direction in try to motivate the extension of your framework to other models that do not have the IID, which of course I understand is quite complicated, right? But in particularly here, we made a small exercise, right? So basically, starting from IID, specifically at Dirichlet process, we consider the two-parameter generalizations, the Pittman process, and we also transform or generalize, choose stick-breaking processes with exchangeable sticks that generalizes the Dirichlet process and the geometric process, which has identical sticks. And the idea is to kind of map the Dirichlet process into the geometric process by tuning a single parameter, right? So we consider these two directions. And here we made a small sensitivity analysis. So essentially what I was talking about is to consider exchangeable sticks. When I make this parameter go to 0, I recover actually the sticks of a Dirichlet process. When I make it go to 1, they become identical. And here, well, the Pittman model, everyone knows it. And we applied it to the very famous galaxy dataset and to estimate the density and as well as the number of clusters. Here, what we can see is that under very small perturbations of rho around 0, so around the Dirichlet, making the making the Dirichlet process sticks a little bit more dependent, or under small perturbations of sigma, we can see that the expected number of clusters varies not too much, but varies a little, and the estimated density does not vary too much. It's important to highlight that this is because the perturbations of sigma are very small, right? So maybe if I move it a lot more, the estimated density will change, right? So in order to do this, we use MCMC. And this is very heavy to do because, well, we already know MCMC tends to be computationally expensive, but also for these more complicated models, MCMC converges slower to the stationary distribution. So it takes even more MCMC samples to obtain these results, which is very computationally heavy. So I think it would be super cool to have your framework extended to other models, not necessarily these ones. This is just too motivated. We went a little bit further to try to see how to do this. So I think that the first step is to actually derive a mean field BB for exchangeable models. For Pittman, I think it's probably similar, but there's a problem, right? When you consider approximating distributions taking this form, I think the hardest thing for the Pittman model is choosing the truncation level K. And for the exchangeable case, I think choosing the shape can be a little bit different, because if you have independent sticks, these three, it's enough to assume this to have this. But in exchangeable sticks, this third equality is not true. You would have to assume it, which if you don't assume it, it complicates stuff. If you assume it, you are making an extra assumption. So we were wondering if you have insight on this, and specifically motivated by the Pittman process, what happens on your framework if one, for example, misspecify the truncation level? Is that too bad? And other thing is, how feasible do you think it is to actually extend your framework to other dependencies, other things except IID sticks? So thank you. I will leave the word to the next discussant.
Excellent. Thank you, Maria. Again, very well timed. We're all extremely well behaved this afternoon. So we have the final discussion, which I think Filippo Ascolani will give. At least that's what Maria.
Yes, exactly.
That's what Marta told me. Yes.
Yes, you should see my screen.
Yes, we see it. It's a little bit small. If you make it bigger, even better. Wonderful. Yeah. Very good.
So thank you very much. So today's work dealt with the problem of specification of the prior that is crucial in Bayesian statistics, both from a philosophical perspective and also from an applied standpoint, since we want to know the impact of our prior distribution on the conclusion. And this is particularly relevant in Bayesian nonparametrics, since we are placing a prior on an infinite dimensional object. So what this paper gives us is a general framework to conduct a sensitivity analysis, both with nice theoretical guarantees and still with computational scalability. So we believe that this is a very impactful work that will lead to new research directions. In particular, the work focuses on mixture models in which the BNP prior plays the role of the latent mixing measure. And so in this sense, due to the discreteness of the Dirichlet process and the other stick-breaking priors, we have a discrete latent structure that is often very relevant in application because it allows you to perform model-based clustering. And it is very useful for practitioners, as we saw also in the presentation. So the three main objects that is natural to study when doing sensitivity analysis is the density estimate. That is probably the main goal if you're using a mixture model. And then you have this latent clustering structure. And finally, some functional, like the number of clusters, the co-clustering metrics, and so on. So one may wonder which of those 3 points depend the most on the prior specification. And in order to understand that, we consider a very simple example that is studied in the paper by De Blasi and co-authors, in which they consider 50 observations that are IID from a mixture of 2 normal distributions. They fit different prior specifications that came from different BNP priors, so a Dirichlet process, a Pittman process, and so on. All set so that the expected number of component in 50 observation is equal to 25. So it is a kind of prior misspecification. And here in this plot, you can see that the density estimates are very close. It is very difficult to distinguish among the different posteriors. However, if you look at the posterior on the number of clusters, you see very different behavior. So if you have a Pittman prior, you have that the number of clusters concentrate on the true one that is equal to 2 in this case, while if you consider a Dirichlet process, you still have a high posterior mass on a higher number of clusters. and a high number of clusters. And it is essentially due to a lack of identifiability, because you are able to fit the true density with a very different range of number of clusters. So this is an example of the general fact that this functional and more in general, the clustering structure is very delicate with respect to the choice of the prior distribution, especially if you go beyond the Dirichlet process. So we believe that the choice of the author to focus on this clustering structure to perform the sensitivity analysis is very smart and actually very insightful. So we wonder how the approximation that the authors need to do in order to perform the computation impact this clustering structure that we see that is very delicate. Indeed, the authors need to truncate the stick-breaking representation, and this threshold is chosen to have a good approximation a priori, but we have in principle no guarantees that will be a good approximation a posteriori. Moreover, if you want to study the number of clusters, if n grows, then in principle also the threshold should grow, but it's still not very clear how to make K-max grow. And here the main point is that we lack a theoretical knowledge of how the number of clusters behaves a posteriori. Similarly, the authors use a variational approximation using the reverse Kullback-Leibler divergence that allows for very quick computation. And here we wonder whether being close using this divergence means also being close in terms of clustering structure. And once again, the problem in answering these questions, in our opinion, is that we know very little about the posterior distribution on the latent space of clustering structure. So just to wrap up, assessing sensitivity is crucial in Bayesian nonparametrics, and we saw a simple example that highlights that the clustering structure may be very delicate with respect to the choice of the prior. And therefore, we believe that this method is one of the best that we have with our knowledge to assess the sensitivity. And our final takeaway is that in order to do better than this, we would need much better understanding of the theoretical processes of the posterior distribution on the latent space. So congratulations again on the nice work, and thanks for the attention.
Wonderful. Thank you very much, Filippo. Now we have a little bit of time for Ryan to come back with a rejoinder, which hopefully we can fit in 10 or 12 or so minutes if you can, Ryan. You're still muted.
Okay, can you hear me?
Yes, now we can.
All right, thank you. And can you see some slides?
Yes.
Has the word rejoined? Okay, right. So sorry to be repetitive, but I just want to say thank you again to the respondents. This was, for me, just like such a wonderful learning experience, and I really got a lot out of reading what people wrote. I thought everyone had really fantastic, insightful things to say. And I basically agree with everyone, really. I think a lot of very interesting questions have been raised. So we observed roughly 3 categories of observations, or you might call them pointed questions in the responses. Well, first, would a different model or a summary statistic be more or less robust in the Dirichlet process or the expected number of clusters? Second of all, can or even should one form variational Bayes approximations to different models from the BNP literature? And I think implicit part of this is also, some concerns about the validity of truncation when you form these approximations. And finally, can one form a local sensitivity metric to different quantities of interest, modeling or fitting parameters, different posterior approximation procedures, or some combination of all of these? So I think questions in the category 1 or 2 are very natural and important. And I think there are a ton of great ideas and important concerns. But I'm going to focus on questions in category 3. Because I think that constitutes our paper's most distinctive contribution. So what kinds of things did folks suggest local robustness techniques for? I had to use a small font to fit them on the slide. There were a lot of them, and this is probably an incomplete list. Can we form local robustness measures for case influence, the loss function, exchangeable stick-breaking processes, empirical Bayes procedures, generalized Gibb priors, local mass preserving priors, and so on? So in our rejoinder, it was supposed to be a short rejoinder. So we derived local robustness metrics for the first four, the ones marked with pluses. And we think the others are great ideas, and we suspect they're comparably tractable. However, just deriving a local robustness metric, which basically means computing a derivative, is actually, I'd like to argue, a very small part of the work that would need to be done in order to provide useful local robustness techniques. Showing that your local robustness metric is useful is actually much less straightforward. So in this context, I would like to mostly provide what I see as a roadmap for answering these questions. Can you provide local robustness metrics for all of these different settings in the context of what we've done here? So what is the local robustness recipe? Well, there are three things that you have to do, but you have to do these kind of whether or not you're doing local robustness. First of all, you have to write down a model parameterized by some hyperparameter we'll call omega that you're interested in maybe changing. So in our paper, omega might be the concentration parameter alpha of the Dirichlet process. Second of all, you have to define an estimator that you're interested in. That estimator will be a function of omega. For example, it might be an optimal variational Bayes approximation. Third, you have to actually estimate your estimator for some particular value of that hyperparameter. I'll call the particular value omega naught. So for example, omega naught could be your choice of alpha in the Dirichlet process, and you approximate theta hat by running an expensive numerical optimizer. This is all stuff you had to do anyway. How do you do local robustness in this context? Well, step 4 is you have to compute the derivative of your estimator with respect to that hyperparameter and use it to form an approximation to the map from that hyperparameter to your estimator. And typically that takes the form of a first order Taylor series approximation as given here, right? Second, and important, just like very importantly, you have to check that this approximation is good. How do you check that an approximation is good? Well, it depends on how you intend to use it. So you need to say how you intend to use it and then check it on those terms. And I'm going to argue here that step 4 is actually often pretty straightforward, especially nowadays. And step 5 constitutes the real work to be done for local robustness. And so why do I say step 4 is straightforward? Well, there are two kind of big settings that we often use in statistics, including Bayesian statistics, and both of these settings have pretty automatable derivatives in the same context as in the same way that our paper uses relatively automatable derivatives. The first is estimators that are solutions to systems of estimating equations. That is, our estimator theta hat is a value that sets some system of estimating equations which themselves depend on our hyperparameter to 0. So smooth optimization problems are in this category. G would be the gradient of your objective function. When we choose parameters that set that gradient equal to 0, variational Bayes fits, which are approximated with numerical optimization, take this form. Another thing that we do a lot in Bayesian analysis especially is our parameter of interest is a moment from a distribution which we only know up to a constant. So we'll call that theta hat samp. It's an expectation over a distribution of parameters zeta given some data x, and again our hyperparameter h of some function h of those zeta. Our hyperparameter omega of some function h of our parameters. So an example is posterior means, and we might approximate this with Markov chain Monte Carlo. And I want to emphasize that both of these very general formats have straightforward and automatically computable derivatives. And we give their exact form in the rejoinder. They're well known in the literature, but we just want to really call attention to the generality of with which you can automatically compute these derivatives. So what do you need to compute the derivative of the solution of a system of estimating equations? Well, you need a software implementation of the map from theta and omega to this estimating equation, and you need an initial optimum. That's it. Automatic differentiation can take care of the rest. The computational challenge here is the solution of a potentially large linear system. If you're computing posterior moments, you need a software implementation from your posterior parameter zeta and your hyperparameter omega to the log joint distribution of the data and your parameter zeta. You don't need to be able to normalize this. And you need MCMC samples from that posterior. And here the computational challenge is Monte Carlo sampling error. Now, once you have these two things in hand, a lot of things become smooth combinations of these. So for example, empirical Bayes estimates typically combine a posterior moment estimate with an optimization problem. If you want to parameterize sensitivity to densities, you parameterize a path the way we did in our paper, and then you could use these tools. So these are super widely applicable. Now, the more difficult part is asking when they're useful. And in order to ask whether it's useful for your particular purpose, you need to say what you were trying to do. And in our paper, what did we want to do? We wanted to use these local approximations to quickly explore the space of stick-breaking priors, ideally before actually verifying your results by actually refitting. So if that's your goal, what do you need? Well, you need to be able to efficiently compute the derivative. So we discussed that in our paper by focusing on solving the large linear system, basically by using conjugate gradient and closed form indicator updates to reduce the dimensionality of the linear system. You need to be able to interpret the derivative, right? So we really emphasized allowing the user, through use of the influence function, for example, to visually assess whether a proposed perturbation is reasonable or a particular measured sensitivity is excessive and worth worrying about. And finally, maybe most importantly, you need to establish that the derivative is actually able to extrapolate reasonably well. In kind of traditional language, you have to establish that the local robustness metric is a good approximation to the global robustness metric. And I think our Frichet differentiability concerns were part of that, but probably the big part of that was actually doing a bunch of experiments by refitting and showing empirically that it does reasonably well. Now, I want to call attention to what we did not do in this paper, which is we did not use these derivatives as measures of robustness per se. And I call attention to this because I think a lot of the classical literature to which we're deeply indebted sort of takes this as its ambition. And I think we don't we don't live up to this use case. So for example, even if you kind of pass our tests, there may be posterior quantities which you don't consider, which are actually very sensitive. In some sense, we're not even trying to check the whole model for robustness. We're only checking the stuff that you care about. We saw some of these worst case density prior perturbations. They look kind of unreasonable, right? So we want to encourage users not to just look at the worst case sensitivity, but also to look at the corresponding prior and decide for themselves whether that actually corresponds to a subjectively worrying prior perturbation. And finally, there were certainly occasions when our linear approximation actually wasn't that accurate. So whenever possible, these approximations aren't perfect, and it's good to approach them critically and, if possible, to refit before drawing conclusions. So providing kind of like universally valid context-free measures of robustness with derivatives is ambitious and important and really valuable, but it's also in a lot of ways more difficult than what we attempted to do. And I actually think part of our value here was specifically in narrowing the scope of our ambition, to providing diagnostic tools rather than trying to provide something that is much more widely applicable. So here are the takeaways in the decreasing order of importance as I see them. First of all, there are a ton of exciting potential applications for local robustness. I think the responses really called this out. I think that's true. Computing these derivatives is actually pretty straightforward and highly automatable. I'd encourage everyone to go out and do them themselves. And then finally, showing that the local robustness metric is actually useful for its intended purposes, often the most difficult work. And again, a big thank you to the editorial board and all of this discussants for this wonderful process. I really enjoyed it.
Thank you very much, Ryan. That's extremely well timed again. So wonderful. I'd like to open the floor to anyone else that has a comment or wants to sort of ask a question or contribute to discussion at all. I don't see anything in the Q&A section, unless Tommaso can correct me. Am I looking at the wrong thing? Or is there indeed nothing at the moment?
Nothing at the moment.
Okay, so
now there is one. There is one.
Ah, there is one. Good. Okay, that's great. We can actually perhaps do you want to talk in this particular sort of meeting, or do you prefer the this thing to be dealt with by simply me reading it out? I'm assuming that's the case. So in this case, well, Ryan, can you see this or not? If not, I can
see it. I can see it. Yeah.
Oh, you can see it. Okay. So for those who cannot, I'll just read it. So thanks to Ryan for the great presentation. The question is whether the results that you presented assume that the mixture likelihood is correctly specified, and if we can use a similar approach to assess the sensitivity of results to the choice of likelihood. Okay. Is there any comment that you can have in response, Ryan?
No and yes. It's there's absolutely nothing about correct specification. I mean, I think it's use strong language. I think it's absurd to assume that some of these models are correctly specified, especially the tied to thrush, right? It's a numerical procedure that we use as a summary statistic. I think correct specification doesn't come into it, and it just doesn't matter. We're differentiating a procedure that you use. We're assuming that procedure is meaningful to you, and we're computing its sensitivity. That's all. As for sensitivity to the likelihood, absolutely, you do the same thing we did. You take the likelihood, you parameterize a path, you differentiate, you check it for usefulness, and particularly for shape differentiability. And actually, like, now that I have, through this process, learned more about Bayesian nonparametrics, and particularly after reading the responses, I'm kind of kicking myself for not doing the likelihood instead of the stick-breaking prior. I think that would have been a better subject for this paper. Maybe someone will do it, maybe we will do it. But yeah, I think that's a fantastic and very, very useful suggestion.
All right, thank you very much. Do we have any other comments or questions from anyone that's still online? Or indeed from any of the people that have sort of spoken already. If you have any brief comments that you want to get in, feel free to do so now. We are roughly at the point where of course we start to drop participants because it's sort of dragging on for an hour and a half almost. But I'm happy to entertain anyone who has a quick point to make. Not at the moment. Okay, wonderful. Then let me thank all participants to the sorry, to the webinar, especially of course the speakers who've given us really some extremely thoughtful and insightful contributions. These are very powerful ideas, I think, and I would expect them to be quite influential in years to come. So I want to thank you very much for this extremely interesting webinar, which also, by the way, was very clearly presented. So it's quite a challenge to do that, I think. So thanks to all of you, and I hope to see you again in a future webinar, which is still not quite scheduled, but we will keep you updated on when the next one is to be expected. Okay, so thank you very much, and have a good morning, evening, depending on where you are. Okay, thank you. Take care. Bye-bye.